Hi there, this is Dr. Everybody with Project 4. So, what are we doing here? We've got, so this project we're going to be using functions, and of course things from previous projects like strings and integers and loops and all that good stuff. The topic of this project is compression. You use compression all the time. You do a zip file, that's compression. You take a picture on your phone, it gets saved as a JPEG, that's compression. You make a video that's an MP4, that's also compression. So you're doing compression all the time. So in this project, we're going to take a look at a particular compression algorithm. But you'll kind of wonder here. What you'll notice that sometimes we compress the file or we compress a string, and it actually turns out to be bigger than what we started with. That's because these are designed rather than to handle 20 or 40 bits like we're doing. It's they're designed to have an impact when there is millions, billions, or trillions of bits. So let's take a look at it. The idea here is that we have a imagine that we have a picture, right? And it's got it's black and white, so we can represent the blacks and whites as bits, zeros and ones. Normally, if it's actually a photo, you'll still have pixels like this, but rather than single bits, you'll have 8 bits, 24 bits, whatever, representing colors and things like that. But we're simplifying this, so something like 8 by 8 bits might be represented as a string like that, right? Where bits, where you have 1 for a dark bit, 0 for a white bit. Now, let's what we're doing here is it's called run length image compression. So let's take a particular example here where the first 16 bits are white, the next 16 bits are black, and so on. And if we represent this as a string, it will be 16 zeros, 16 ones, 16 zeros, and 16 ones, such as we have here. All right? Looks like that. Kind of a silly way of a silly kind of example, but it will give us something to work with. Now, the way this type of compression works is we're looking for, we're going to count how many zeros and ones that we have, and we'll hold on to the count. So what I'll do is we've got a bunch of zeros here. How many do we have? We have 16. So I record that as a 0. And then we take the number 16 and we represent that in binary, which is 1000, and then we fill in zeros to make this 8 bits or a byte every time. So this right here says that we have 16 zeros. So 16 zeros took us up to here. Now we've got ones. How many ones? Well, in fact, we have 16 of those representing the blacks. So again, we say, all right, we have 1, or we're now doing ones. We have 16 of them represented in binary, and then we have 2 filler bits. And then we do the same thing again, bunch of zeros, bunch of ones. And one of your tasks is to write a program that will do this. It will compress a string, and then it will also decompress a string. So if I go down, further down into the project, you see that we're going to have a function, and you have to do it just like we say, because we're going to be testing it like this. And it's going to take in a string of bits, and it's going to compress it and give us in return a string of bits. And then we'll also have the reverse process. Take the compressed string and reverse, okay, uncompress or decompress, however you want to write that. And let's take a look at how this algorithm is going to work. All right. So what you're going to do here is you're going to write we're going to write a loop. It's going to go through, so we've got a string. It's got quotes on it. And we're going to loop through that, and we want to start with this string, and we want to end up with this string. How do we go about doing that? Well, we're going to start with this index and figure out how many zeros we have. All right, so we're going to start with zeros, record the 0, and then we're going to do a count. And so what might my program look like? Well, if I have a while loop and some kind of an index, all right, I can start with my index at 0, and there I find that I have a 0 at index 0. Now what I want to do is I want to loop through here, and I want to have a count. Right. And oops, I want to count how many zeros there are. So my count will start at 0. I'll have another loop. I'll have a while loop inside my outer loop, because I don't know how many I'm going to be counting here. And I'll just keep looking. Increase the index. Oh, still got zeros, still got zeros, still got zeros. And each time I do that, I go, I add 1 to my index, and I keep going, checking these, check, 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 check. Ah, I hit a 1. And now I've made a count, in this case 16. I take that 16 and I convert it to binary, and we'll write a function to do that, but keep an eye on that, right? So that'll, we'll have that function. Give it a 16, it'll give me back the binary, which is the 1000. We know this has to be 8 bits long, because that's how this encoding scheme works. So it starts with a 0, it ends with the 16 in binary, and so we got to pad it with 2 more zeros in there. Okay, so now I've found ones. Come around again, and we start the process, except this time I'm starting with 1, and I'll just keep increasing my index and keep going around and around. You keep in us, we're still finding ones, still finding ones, still finding ones, still finding ones. Whoops, I found a 0. So that's how my while loop will end. Again, I now have a count. Better have started that count at 0. And now I make a record of what I found. I put a 1. I put I convert my 16 to a binary, and then I pad with a couple. Now, it turns out that in this silly example, everything is 16. We don't, that will not be the case when we're testing, right? We have no idea how many zeros and ones there'll be, and you'll have to take care of that. So we keep going through here until we're all done. We've taken care of this. Now, if it turned out this time I had 4 clusters of things, it might have been that this just alternated 1 0 1 0 1 0 1 0, and so I've got 64 bits here, and I will then have 64 of these bytes, so I could end up with a very long string there. It is sort of compression. Now, when you build this byte, okay, it's going to start with a 0 or 1, all right? And so you have something at the beginning, and then you're going to put a number on the end, and then you're going to pad it, and you're building a string. And so you'll want to think about, there's a million different ways to do that. There is, for example, there is a string function called zfill. That might be helpful for filling in, because we're always going to be filling in with zeros there. And it's always going to be 8. All right, so there's an idea of how that algorithm will work, and that is what will go into your compress function. What happens with the uncompress? All right, what do we do in reverse? Well, in reverse, we're just going to do the opposite. I'm going to start with this string and end up with that string. And so I know that these will be 8 bits long. So I'll look at the first one. I've got some zeros. Now I've got a number in binary, so I will convert that to a decimal. And guess what? We'll have a function that will do that. And then I say, okay, I got some zeros. I got 16 of them. Loop through 0, 0, 0, 0, 0. Pack that into my string, and we'll use concatenation, the plus of strings. And that's how you will do the decompress. Now, I talked about this business of taking a 16 and making it into a binary number. Well, we're going to have a function that does that. And that's what this one is. We call it num to base. And so that would start with, for example, the number 16 and a base of 2. And then it will output this string that represents 16 in base 2. And we tell you how to do it. All right. Suppose I've got the number n, which is 29. Yeah. What we're going to do is a series of divisions, and we're going to find the quotient and remainder. Remember, quotient is a double slash, remainder is the percent sign. Right? So I'm going to take my number and my base. Right? In that case, the base is, so in this example, the base is 2. I'm going to do the quotient, which is 14, the remainder, which is 1. Right? And I keep going through, and then I take this quotient, and that now becomes my numerator over here. Do the same thing. Find a quotient and remainder. That becomes my new numerator. We get a quotient and remainder. Again, that becomes my new numerator. And so my previous quotient always becomes my new numerator. And the result is the sequence of ones and zeros in order, in the case here, from bottom to top. So my 29 in binary is 1, 1, 1, 0, 1. 1, 1, 1, 0, 1. Okay? That's it right there. All right. And so if I'm keeping track of my result, I'll call it X here for right now, that'll be a string. It'll start empty, and you will be adding on to that. And you'll notice here you want to be adding on to the left. So the first thing you do is you put a 1, and then when you add the next one in, you add it on to the left. And that's, if you think about it, it's not very hard to do with the strings. The other thing to think about here is what happens with, how do I handle this business here where the 14 was the quotient and then it becomes the numerator? Well, if I called my quotient Q, then at the end of my loop, after I've calculated the quotient and remainder and I'm getting my result here, I will just say, okay, now my n equals Q. And then I can do n divided by 2 and n percent 2 and work my way through it that way. Again, we don't know how long it's going to take, but we keep going until my quotient is 0. So again, I'll have a while loop. And I'm going to keep going on that while loop as long as my Q is greater than 0. Right? So there's how you can build you can take this, and you can do it for any base. I did, this example was base 2, but you can just have any base there. The operation is exactly the same. And so there's that function that gives us converting from a string into starting with a decimal, giving us a string in binary or actually in any base. And we want to be able to go the opposite. All right. So in this case, I will be starting with a string of a certain base, and I'm going to get an int out of that. And this works just like you learned in elementary school. So if you have something like a number 135, how is that done? Well, that's 100 and 30 and 5 that you have added together. All right. So and how do you do that? Well, it's 1 times 100, 3 times 10, 5 times 1, because 100 is 10 squared, 10 is 10 to the first, and 1 is 10 to the 0. So there's a consistent algorithm for that, and we do that. Here we have a binary number, 1101, and we the rightmost bit is 2 to the 0, then 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. Again, using, this could be done, same thing be done for any base. Here I'm using an example of B is 2. And so this is actually a lot easier than going the other way. And you'll probably be more comfortable with it because it's very similar to how you were taught numbers back in elementary school. So what I've done at this point is walked you through a bunch of the algorithms. The ones that we need here to convert between bases, and then the compression and the decompression. And then there's a whole nother one here about adding binary numbers. With these projects, we will be giving you a starting code. So it has all the everything that you need in there. It has all the functions and the function names and the parameters and so on. And you have to replace this line. And by the way, get rid of the line. We shouldn't see pass when you hand your project in. This is just a placeholder. Python needs to have a line of code, and pass is a line of code that does nothing. If you're a card player, you can think of it like just the word pass. And of course, you have to have a doc string in there, some string that describes what your function does. Real simple. One sentence does fine. Or if you have a complicated function, you might need to describe it a little more. And we also have a main program, but you want to use this because of those two lines. What those two lines do is when you submit into Mirror, these functions will be tested one at a time. You just submit it to Mirror, and we've got tests in there. And if suppose you're working on this num to base function, and you don't have anything, you haven't done anything to the other ones, of course, all these other ones will fail, but eventually you'll get this one to work. And so you can focus. So this is a problem solving technique where you're focusing on just one part of the problem at a time. Your whole focus is, how do I write this base conversion function? And then once you get that working, okay, so now we'll work on the one going the other way. And then I'll work on compress and uncompress and so on. Right. And by the way, I didn't mention this base to base. This one, it turns out where you're converting a number, say from base 2 to base 10, base 2 to base 8. And what you can do is you've got these two functions already, so you can convert the number from whatever base it's in to base 10, and then convert it from base 10 into the destination. So this function right here, turns out, is like 2 or 3 lines of code. Don't overthink this one. If you don't see it as 2 or 3 lines of code, then you're not thinking about it right. All right, so what does this program look like when it runs? And this is, there's a description in the project that looks kind of long for what goes into the main part of the program. And what it does is it's going to give you this menu of things to do. And this will be like a little bit like what we saw in Project 2. The first one, I can type in either a capital A or a lowercase a. It's going to convert a decimal number to another base. So inside your main program, you will say, give me an n, 14, right? Enter a base. I want to convert that 14 to base 2. And so 14 in base 2 is 1110. Okay. B is actually going let's do a different base. Let's do 14. No, I'm sorry. Well, yeah, suppose I forgot to put 14. It's like, no, we get an error message. Dummy, don't do that. So we'll do notice that either that this will work with capital A or lowercase a, and upper, using the string upper or lower is really nice there. So let's go A. A was not it. I'm already supposed to. I did my A. Okay, I'm blanking here. So let's go 14 in base 8. right? Which is 16. All right, now we can go the other way. So let's do a B. Oh, let's do a B. There we go. Enter a string, and let's see, what did we have? Here was the string base 2. Let's copy that. So there's that, and this is in base 2, and we come back. So that in base 2 is decimal 14. Similarly, I can do this and put in the string 16, say that's base 8, and it should also tell me it's 14. And option C, so the first base will go base 2, and we'll put our base 2 number in here, and that was supposed to be a base. We'll convert 2 to 8. There we go. And now we can enter the string. There we go. And we've taken 1110 in base 2, and that's 16 in base 8. And again, you can do that. You can do your conversion much as we did by converting that first to base 10 and then into base 8. Now, I've forgotten what my menu is, but I have the option M to print the menu. Do the sum of 2 binary numbers, okay? Let's see, 1110, which we know is 14. And let's add 11 to that. Okay, it's 14 and 3. And we end up with the sum being that. Now it's like, oh, well, I wonder what that is in decimal. So we can use option B, and we can take our string here, there, and say that was in base 2, and it says it's 17. So we knew that was 14, that was 3. 14 and 3 should be 17 when we're working in base 10. Okay, next one. So we'll see, we haven't tried E yet. Compress an image. So here's my binary image. Let's have 4 1s, 3 0s, followed by 2 1s. Right. Now let's watch and see what happened. So we end up with a result that is 8 long. I think that's 8. Nope, that's not. I needed to get one more bit. There we go. So 3, 6, there we go. That's 8. And so what are we doing? So we've got a 1, and then we have converted the 8 to binary. And so this is saying we have, I'm sorry, it's not 8 binary. Let's try that again. We found 4 1s, and 4 1s in binary is 100. We use that our conversion function to do that. And so I start it with a 1. I end my 8 bits or a byte with 100, and then I fill in the rest of the bits to get that. All right, then the next, then I have 3 zeros. So we start with a 0. We end with 1 1, which is 3 in binary. We did our conversion, and so there's the next byte. And then finally we finish off with 2 1s. So as before, we have a sequence of 1s, and then at the end we have 2, which is converted, which is 1 0. So that's the final byte. And then we can reverse it if this is working correctly. So we start with that, and it was reversed exactly what we started with. And then finally I can exit. All right. Hopefully that gives you enough to get started on this. Good luck.